Hello everyone, my name is Leszek Mazurek. I'm the author of the paper which proves Collatz conjecture. You can find my paper at ResearchGate.net, the link presented on the screen. I already recorded one video in which I tried to explain my proof from the paper. But even so, I did my best to explain it in the easiest possible way. I was surprised that people were not able to follow my proof and understand it fully. And that's the reason why I decided to record another video, this time the Proof of Collatz Conjecture for Dummies. But now I will be not following my proof, but I will explain the idea that is fundamental for my proof, and it should be enough to understand it after carefully watching this video till the end. When I was doing my research, I checked many different ways how potentially we can prove Collatz conjecture. At the end, I discovered this formula, and I will show in this video that this formula is the key to prove Collatz conjecture. This formula can be presented also in slightly modified way, like this. In my paper, I stated in Theorem 1.1, if a given number n0 has a representation like in this formula, then Collatz conjecture is true for that particular n0 and vice versa. It's very important. But as I said, I will be not following my paper, but explain the idea that constitutes the base for my proof. So in this video, I will answer the following questions. Why is this formula important for Collatz conjecture? How to construct this representation for a number? Can we construct this representation for any number? And finally, why do the 3 points above constitute the proof of Collatz conjecture? I will answer all these questions, but I will do this in a slightly different order. I will start from the second question and follow with the first. The reason for this change is that it will be easier for you to understand it. So I will start from answering question how to construct this representation for a number, and later in the next steps I will explain why is this formula important for Collatz conjecture. Please stay with me till the end to understand the proof. Before we will start answering all these questions, let's talk for a moment about this formula. So our goal will be for any selected initial number n0 to find all these parameters in this formula such that this formula will be correct. So actually we are searching for a representation of this initial number n0 in this form. Let's check what are some special characteristics of this formula. We will comment on the second line pointed here by arrows. On the left-hand side, we have only our initial number n0 multiplied by the biggest power of 3. On right-hand side, we have only one term positive and all other terms are negative. This one is positive and all other terms are negative. Powers of 3 are increasing by 1, as we can see here, 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 and here. This is the biggest one. Powers of 2 are just decreasing, not necessarily by 1. Starting from this number, they are decreasing according to what is highlighted here. Only 2 terms are purely powers of 2. Knowing that 3 to the power 0 is equal 1, we have only these 2 terms which are purely in the form of powers of 2. All these statements must be fulfilled to have this formula constructed properly for our initial number n0. Now we can start with the first of our questions, how to construct this representation for a number. In my presentation, I will use numbers in binary notation. So let's start from such a number. Binary notation means that every digit in this number has a meaning as a corresponding power of 2, like presented. Please notice that these powers of 2 are increasing as we move to the left. So trying to convert this binary number into decimal number, we have to sum up for all non-zero bits their corresponding powers of 2. In our example, this will be 2 to the power 0, 2 to the power 2, 2 to the power 3, plus 2 to the power 6, which is 1 plus 4 plus 8 plus 64, in total 77. So this is standard notation, usually used in binary numbers. But for my presentation, I will use this notation, which is actually almost the same, but the sequence of bits is reversed. So as you can notice, powers of 2 are increasing as we move to the right. Moreover, I will not use normal digits like here zeros and ones, but instead of ones I will use plus sign, and instead of zeros I will just leave a blank. I will replace this standard binary number with my slightly adjusted construct, but the value of this number is exactly the same. I believe it's clear, so now I can replace this standard form with my representation. Let's compare this almost standard binary notation with our formula. we can easily see that it is completely different. We have additional powers of 3 and all terms are connected by minus sign instead of plus like here. What can we do about it? Let's temporarily remove powers of 3. It's better, but still not good. Can we represent a number as a difference between big enough power of 2 decreased by smaller powers of 2? Yes, we can. It is represented here on this image, and as we can quickly check, it is equal 77. But in this form, it is exactly as needed for our formula. So what we've got here is one big enough power of 2 decreased by smaller powers of 2. In our case, we have 128 decreased by 32, 16, 2, and 1, which is 77. These two numbers are equal, even so represented by different bits. So using this proposition, we have two representations of number 77, one as a standard binary notation, and the second, I would call it extended binary notation because it is not standard and we are using not only positive values of bits but also negative. How was this new notation created? Let's compare both. We see that we've added this extra bit at the top. Then all gaps from our standard notation are represented as negative bits in our extended notation. And finally, this lowest bit is extra subtracted, which means that it is also represented as negative bit here at the end. Using this rule, we can convert standard binary notation into this extended binary notation. So here we have a few more examples. Number 99 represented in both notations. In standard binary notation at the top and my extended binary notation at the bottom. So again, here we have this one extra bit at the top, then all gaps represented as negative bits, and also this lowest bit again represented as negative bit. This rule is always valid if you want to convert number from standard binary notation to this extended binary notation. Here again, number 170, again, one bit at the top, all gaps represented as negative bits, and lowest bit also as negative bit. Number 8, the same rule. Here we have number 4. As you can see, we can start this conversion even higher, on higher bits. In this case, we started from 2 to the power 6. Then all these 3 bits are treated as kind of the gaps. They are represented by negative bits here. And this single bit is treated as the least significant bit, which is represented as this negative bit at the end. This is also correct. Both lines represent number 4. Now we know how to build this extended binary notation with only single positive bit and all other negative bits, which is very good because it at least represents partially this expected equation, but it is not all because we still have these powers of 3. My proposition for this is to represent numbers in 2 dimensions, like here. On the horizontal line, we have powers of 2. Vertically, we have powers of 3. For example, if we will take this bit, it should be calculated as 3 to the power 3 multiplied by 2 to the power 2. I will still use the term bit, even so these are not ordinary bits anymore. And another example, if we will take this negative bit here, it is minus 3 to the power 1 multiplied by 2 to the power 5. There is another interesting characteristic of this two-dimensional representation, which is that, for example, if we have this bit, to multiply it by 2, it's enough to shift it one position to the right side. To divide it by 2, it's enough to move it one position to the left side. But also to multiply it by 3, it's enough to move it one position down. Also, division by 3 is represented by move one position up. So this is very interesting representation because just by moving bits up, down, right, left, we can achieve all of these operations. This system that I proposed here for the presentation of numbers in 2 dimensions using powers of 2 and powers of 3 has also some other interesting features. Not like in case of standard binary notation, where every single number can only be represented by one configuration of bits. Here, every number can have many different representations using different configurations of bits. For example, if we will take this bit, we can separate 3 from this 3 to the power 3 and have it as presented. Now we can say that this 3 is nothing else but 1 plus 2. When we will multiply all of these, we've got this result. As we can see, our initial bit is equal to 2 other bits, like presented here. We will call this rule number 1 based on the substitution that 3 is equal to plus 1. We can also have other substitution. Let's start from the same bit. Again, 3 to the power 3 multiplied by 2 to the power 3. Again, we are separating 3 from this term. This time, we substitute 3 by 4 minus 1. Again, when we will multiply everything, we've got our result. So now we converted our initial bit into difference between two bits presented here. So this is another rule, rule number 2, which is based on the transformation that 3 is equal 4 minus 1. Basically, what we did here. Using these two rules, we can show how to represent a number using different configurations of bits. So let's start from a number like presented. When calculating the value of this number, we see that it is 99. So we can assign 99 to this configuration of bits. And now, using our rules, we can transform this number into another version that will keep the same value. We will use this rule number 1, which works not only for positive bits, but also for negative bits. So in our case, this bit here is equal to these two bits. We will apply this rule one more time for this bit. So again, this bit is equal to these two. Now we will apply rule number 2 to our last positive bit like presented. The value of created bits is again 99. So the conclusion is that using these two transformation rules, we can convert one representation of the number to another representation of the same number as presented now on the screen. Now we are ready to search for this special representation of the number in the form presented at the beginning of this video. We will do a very simple example for number 17. Number 17, when presented in the standard binary notation, consists of only two bits, 2 to the power 4 and 2 to the power 0, which is 16 plus 1 is 17. In the first step, we have to convert this standard binary notation into my extended binary notation with only one positive bit at the top and all remaining bits negative. So as you probably remember, this can be done by adding extra positive bit at the top, replacing all gaps with negative bits, and also replacing the least significant bit with another negative bit. We can quickly check that this extended binary notation is correct and represents number 17. Now we can start a special procedure that at the end will produce this required representation of the number. In the first step, we have to multiply our initial number by 3. To do this, in this special two-dimensional representation of numbers, it is enough to shift all bits one position down. Now, using these two rules for bit transformation, we will make a copy of this number in the row above. We will start from first bit from the left side and apply rule number 1. We created 2 bits here. Now we will repeat this operation for the next bit, also using rule number 1. Of course, newly created bits are combined together with the bits that are already there, and that's the reason why this bit is shifted to the right. Now we will apply rule number 1 to the third bit, and finally to our fourth bit. In case of this last bit, we can apply either rule number 1 or rule number 2 just to have one positive bit at the top of this next number. So now we will apply rule number 1 to this positive bit to have this. As you probably notice, this bit here disappeared because there was a negative bit already present in this place. This step is completed. In each row, we have exactly the same number. In the next step, we will again multiply everything by 3 by shifting all bits one row down. Now we will again copy bits to the first row, but this time we will skip the first bit from the left side. So we will start from the second bit. So starting from this bit, we will apply rule number 1 and again rule number 1 to this bit. Now we will copy this positive bit at the top, but in this case we can use only rule number 2. Otherwise we would have 2 positive bits at the top, which is not as required. So after applying rule number 2, we have this. And again, we will multiply everything by 3 by shifting it down. Again, we will copy it to the upper row without the first bit. First bit is always omitted, with a one exception, that in a first step we should start from the first bit. In all other cycles, we are skipping this first bit from the left side. So again here, we are applying rule number 1 to this bit. And again, rule number 1 to this bit. In this case, we can apply rule number 1 because this second positive bit will disappear. And we have only one positive bit at the top, all other bits are negative. In this case, there is only one bit. And now we completed this process till the end. The condition to stop this process is that we have only 2 bits in this first row, like here. Now we can remove some of these bits that were used during the process, because we don't need them anymore. As a result of this process, we have these remaining bits that reflect exactly this required representation of the number. This is the general formula, and this is a specific for our case formula. We will check if this representation is correct. So all these bits here that we omitted at each step, and these last 2 bits constitute this special representation of the number. We will check all conditions for this special representation. Condition number 1, on the left hand side there should be only our initial number multiplied by the biggest power of 3, and it is here. It is easy to see that this number we started from here is multiplied by the biggest power of 3, which is 3 to the power 3, like presented at the bottom. The second condition is that on the right hand side we should have only one term positive and all other terms should be negative. So we've got here this positive term and all other terms are negative. Also you can check it here, only one positive term and all other terms are negative. Powers of 3 are increasing by 1, starting from 3 to the power 0 in this term. Next is 3 to the power 1 in this term. Next is 3 to the power 2 in this term, and finally our highest power of 3 on the left side. As you can see, all powers of 3 are increasing by 1. Condition number 4, powers of 2 are just decreasing, not necessarily by 1. So we'll check. We are starting from 2 to the power 9. Next we have 2 to the power 5. Next we have 2 to the power 2, and finally 2 to the power 0, exactly as required by this condition. As you can see, all these powers of 2 are decreasing, but not necessarily by 1. And finally, we've got condition number 5. Only 2 terms are purely powers of 2, which are these 2 terms. We have confirmed that this created by us a representation of number 17 is correct. Now it should be clear how to construct this representation for a number. Now we can move on to our next question. Why is this formula important for Collatz conjecture? We will clean unnecessary elements from the screen. Once again, what we have here is our initial number 17 multiplied by 3 to the power 3, and it is equal to this special representation highlighted here. In the next step, we will divide both sides by 3 to the power 3. So now on the left hand side we have 17, and on the right side we have a slightly modified formula. As you probably remember, division by 3 can be achieved by moving all bits up. But we can also achieve the same by moving the powers of 3 down as presented. So now what we have here is actually highlighted at the bottom. We've got our initial number 17 back, and all these terms are here. We can quickly check that we are starting from the term 3 to the power minus 3 multiplied by 2 to the power 9, which is exactly this bit, minus all these 3. Let's remove all unnecessary things from the screen. We have only this special representation of the number 17. So now we will do the following process. We will multiply all these bits by 3 by shifting them one line down. We will add 1 to this number. By adding 1, this bit will disappear. Now we can divide this number by 2 to the power 2. As you remember, division by 2 is realized by shifting to the left, and we have to shift twice. And again, we will multiply this number by 3. We will again add 1. And now, as you can see, we can divide this number by 2 to the power 3. And again, we can multiply by 3. We will add 1, and finally we can divide this number by 2 to the power 4 to have 3 to the power 0 multiplied by 2 to the power 0, which is actually 1. So in this way, starting from our special representation of number 17, we went to 1 via a process described in Collatz conjecture. And that's the reason why this special representation of the number is critical to ensure that the number can be successfully processed to 1. So I believe this is the answer to the second question. Why is this formula important for Collatz conjecture? And now it should be clear that if we can represent number n0 in this form, it can be easily processed to 1 via the process described in the Collatz conjecture. Now, before we will continue with our final question, which is, can we construct this representation for any number? Let's do a few more complicated examples using a specially prepared macro in Excel. Here we have this Excel with two-dimensional space for number representation. At the top, powers of 2, on the left side, powers of 3. You should remember this from the previously presented slides. In the upper part, there are some other elements, which I will explain in a moment. Now we will do a presentation for number 39. To start the presentation, we need to provide in this field our initial number, which is 39. And now it's enough to press this button start and Excel will do everything for us. But for presentation reasons, I will explain every action step by step. Now I will initiate the macro by pressing button start here. So at the beginning, this our initial number 39 is converted to the standard binary notation here. We can quickly check that it is correct. 32 plus 4 plus 2 plus 1 is exactly 39. And now we have to convert this standard binary notation into extended binary notation with only one positive bit at the top and all other bits should be negative. In the next step, we have to multiply this number by 3 by shifting all bits one line down. Now we have to copy this number to the line above, starting from this first bit from the left side, using two previously defined rules. With a remark that for negative bits we can only use rule number 1. We use rule number 1 for the first bit, now rule number 1 for the second bit. Again, rule number 1 for this bit. Finally, rule number 1 for this bit. Rule number 1 is preferred over rule number 2 for positive bits and should be used whenever possible. Now we have to again multiply everything by 3 by shifting all bits down. Now in the second iteration we will again copy this number to the line above, but this time we will skip this first bit from the left side. And we will start copying from applying rule number 1 to this bit. And now to this bit. In this case we have no other choice, but we have to use rule number 2 to copy this bit to the upper row. And again, we have to multiply everything by 3 by shifting all bits one line down. We will copy again this line to the line above, starting from second bit. So this bit will be just marked as the one from the result. And now we will copy this bit to the line above, again applying rule number 1. Now for this bit, Now we will apply rule number 1 for this bit and finally for this positive bit. Here we will apply rule number 2. Again we will multiply everything by 3 by shifting all bits one line down and so on and so on. Now I will continue all these operations with the full speed of the macro just to complete this task till the end. Here we have the result of this macro, our initial number 39 and its special representation required to ensure that this number can be easily processed to 1 through the process described in the Collatz conjecture. In two versions, one Excel notation for easy verification that this result is correct and this number is equal to this special representation, and LaTeX version below. There are few important things that I would like to mention again. First of all, there are two rules that can be used for positive bits to copy them to the upper row. But rule number 1 is preferred over rule number 2 and should be used whenever possible. It is important that in every row we should always have only one positive bit at the top and all other bits should be negative. for all negative bits, only rule number 1 can be applied. There is also another important thing. During this whole process, when we are copying bits from one row to another, only during first iteration, we are copying all bits. Starting from the second iteration, we are always skipping the first bit from the left side and copying only remaining bits. This is very important because all these omitted bits constitute our final result, which is this required representation of the number. Now we will check if this result is really correct. Usually to do this, I use full precision calculator from the internet because these numbers can be extremely big. But in this case, it's enough to use Excel to check that the left side of this equation is equal to the right side. So let me do this calculation quickly. So here on the left side, we have this number, and on the right side, we have this number. As you can see, this calculation is correct, and the left side of equation is equal to the right side. There is also another macro implemented in this Excel. Using this macro, we can process a number from its special representation to 1 through the process from Collatz conjecture. Exactly the same way as it was previously presented on a slide. So I will now initiate this macro by pressing this button here. As you probably remember, it will start from division by 3 to the power 11. So I will divide all these bits by 3 to the power 11. Division by 3 means shifting all bits one row up, and we have to do this 11 times. But the equivalent operation is to adjust these powers of 3 on the left side. Now I will remove all unnecessary bits from here, which are not part of the solution. Please notice that here we've got 3 to the power 0, which is 1. Therefore, this is exactly the representation of our initial number 39 in the form of extended binary notation. And above you can see the special representation of the same number. After removing this, what we were left with is only the special representation of number 39, with which we can start this process. In first step, we will multiply by 3. You can observe all the steps here. Now we will add 1. Now we can divide by 2. And again, we will multiply by 3. Plus 1. Divide by 2. Okay, please notice that all steps done here in this space are registered here. So as you can see, we started from multiplication by 3, then plus 1, divided by 2, again multiplication by 3, and so on and so on. So in this way, this special representation of the number, all these bits are processed to 1. Now I will continue this macro in a full speed to complete this process faster. So finally we have reached 1. We started from this special representation of number 39 created in the previous step, and we went through all the steps according to the Collatz conjecture, finally reaching number 1. Before we will continue with more complex examples, let me explain a few other options that we have here in this Excel. First of all, instead of starting with a number in decimal form, we can also start with a number in binary form. To start with a number in binary notation, we have to provide this number here. In case both numbers are provided, a number in decimal form is ignored. So we can start, the macro is running, and this is our result. As you can see, here we've got the number in binary notation that we started from. There are still two other options to explain, which you can see here. This is our previous example for number 39, and I will quickly explain these options. First option is the mode in which this macro is running. So mode 3 you can see right now, but there are also 3 other modes. For example, mode number 1 is generating just a pure result without all these unnecessary bits. Mode number 2 is not only producing this result, but also keeping all these positive bits. And number 4, which in every iteration uses the substitution that 3 is equal 4 minus 1 for every positive bit. So as you can see, there are sequences of negative bits just after these positive bits. At the end, as it was presented previously on the slides, if we've got one positive bit at the top and the sequence of negative bits, we can substitute it with this positive bit, which is the beginning of our result. Let's switch to mode number 3. This 0 means this procedure will stop exactly when the final result will be reached. But we can continue this procedure because there is no physical limit and we can still process a few more iterations. For example, if I will ask for 7 more, you can see that additional 7 iterations were produced, and also a new special representation for number 39 is generated. This situation reflects a real case from Collatz conjecture, that we can stop our process not on the first, but on the second or any other appearance of the number 1. When we have number 1 at the end, we can still continue the process, multiply it by 3, add 1 and divide by 4 to get another one. We can repeat this cycle as many times as we want. The cycles at the end are reflected here in a way that for our initial number we can have many special representations that ensure that this number will be properly processed to 1 according to the process described in the Collatz conjecture. You can download the Excel file I'm using in the video from the link in the description below. By downloading the Excel file, you will not only be able to check all the presented examples on your own, but also try out your own examples to see how they work. Let's do another example, this time for the number 27. As you can see, in this case, this process is slightly longer than in the previous case. Even so, the number seems to be similar. Now we will check using a full precision calculator from the internet if the generated result is correct, if the left side of our equation is equal to the right side. I will copy this number to the one instance. Here we got the result, and also this number to another tab to see if this result is the same. So as you can see here, value of the left side of our equation is equal to the value on the right side. It means that this special representation of the number 27 was generated properly. Please notice that all these positive bits are laying on a straight line as presented, which is not the case regarding these negative bits which constitute the result. It looks like that these positive bits are in the perfect order, while at the same time these bits from the result are distributed in a very chaotic way. Let me explain the reason why we have this straight line here going through all these positive bits. Here we have our two-dimensional space with powers of 2 at the top and powers of 3 on the left side, but forget about powers of 3 for a while. We've got just a single bit here at the bottom, and we will perform a number of iterations on this bit. In each iteration we will multiply this bit by 2, which means we will shift it one position to the right. So after the first iteration, our bit is shifted to another column, which reflects multiplication by 2. Now we will do another multiplication, again multiply by 2, and again multiply by 2. After a number of such multiplication by 2, we will achieve this straight line. We can say that this straight line represents a horizontal increase by a factor of 2 per each iteration. Let's start from the beginning, but this time we will multiply by 4, which means in each operation we have to shift this bit 2 columns to the right. So repeating this multiplication by 4 a few times, we've got this, and finally we've got this line, which represents a horizontal increase by a factor of 4. So in each step, our number is multiplied by 4. Now let's check our result from the Excel, which we have obtained when searching for this special representation of the number 27. We have it here. You can clearly see now that this straight line, which is going through all positive bits, represents a horizontal increase by a factor which is less than 4 and greater than 2. As I will show in a moment, this line represents an increase by a factor of 3. Let's carefully check this initial part of our process. For better visibility, we can make it slightly bigger. We started our process from these bits. Our task was to copy all these bits to the row above. We did it by applying rule number 1 to negative bits, and in this case rule number 2 to this positive bit. But in fact we divided this number by 3, shifting it one row up, And to keep this number the same as the one below and compensate this division, we had to multiply it by 3 in this direction. So actually we started from this number, then shifted it one row above, which reflects this division by 3. To have here exactly the same number, we had to multiply it by 3 in this direction. And that's exactly what our rules were doing. In this way, we created this number and we repeated this operation multiple times. We again shifted this number to the row above, which means division by 3. But to keep the same value, we had to multiply it by 3 in this direction to create another number. And again and again. So we again divided by 3, and again to keep the same value, we multiplied it by 3 in this direction to have this number. It is not exactly precise because in each step we omitted these bits, first bits from the left side, the least significant bits in every row. But their influence on our positive bits is minimal because the distance between them is significant. And I will show in a moment how small is the impact from these bits to the increase rate of these positive bits. Let's go back to our Excel with the result produced for number 27. Here we've got our Excel with the result produced for number 27, as you already know it. And I specially generated this in a way that in every iteration, all bits were copied to the line above. So here all bits were always transferred through our rules to the line above. But the point here is that this line going through all these positive bits is exactly the same like here, regardless whether we skip these first bits or not. If we copy all bits, we've got this line. And if we skip in every iteration this first bit, we've got this line, which is actually the same. Now it should be clear for everyone that this line going through all these positive bits represents a horizontal increase by a factor of 3 per each iteration. Please notice that here we are talking about a factor of horizontal increase. So like looking from the perspective of powers of 2. And that's the reason why we can only have a quantified increase in the form of power of 2 per iteration. It means that if we have an increase by a factor 2 to the power 1, we have shift by a single column per iteration, like here. If we have an increase by a factor 2 to the power 2, which is 4, we have shift by 2 columns per one iteration, like here. And to keep this factor of increase at the level of 3, we've got a mixture of both. You can see in some iterations an increase by 1 column, and in some other iterations you can see an increase by 2 columns. It means that we've got here a mixture of increases by a factor of 2 in some cases and increases by a factor of 4 in some cases. But as a result of this mix, we have an average increase by a factor of 3 for all these positive bits. Let's consider the same example for number 27 using mode 4. As you should remember, in mode 4, these positive bits are transferred to the upper row using rule number 2 only. That's the reason why all these positive bits created here make up this straight line, which represents an increase by a factor of 4. Because in each iteration we are using a rule that 3 can be achieved by a substitution 4 minus 1. But we still have this other line visible here, which represents increase by a factor of 3, which goes through the last bits of these consecutive sequences of negative bits just after these positive bits. And as it was explained previously, if we have one positive bit followed by a consecutive sequence of negative bits, it can be easily substituted by one positive bit at the end. We can compare it with the previous result. Now I believe that everyone should understand why all these positive bits are aligned and constitute a straight line, which represents horizontal increase by a factor of 3. Let's talk about all these negative bits on the left side, which contribute to our solution to the special representation of the number. To explain a few important remarks, I will again use this slide previously presented. First of all, we can make an observation that a bit which is second from the left side in one row becomes first in a row above in the next iteration, like here. And we can see it also here and here and here. In all these cases, second bit from the left side becomes first in the next iteration. As a result of this, we also have different horizontal increases from iteration to iteration. For example, here we've got an increase by a factor of 2, but here we've got an increase by a factor of 4, and again by a factor of 2, and again a horizontal increase by a factor of 4. All these elementary increase factors, as presented here, will have an influence on the average increase factor, which is presented here as this black line. Let's switch back to our Excel. Why is this average increase factor important? If this average increase factor were too small, then this process would never end. For this process to stop, the condition must be fulfilled that these two bits are close to each other. And if this line, which represents an average increase factor of these negative bits, will be divergent to this line, which represents an increase factor of positive bits, these two lines will never intersect and we will have more and more different bits between them. So a condition for this process to stop is that this average increase factor for negative bits must be greater than 3. Only then can these two lines intersect. And we can have this algorithm completed till the end. To understand why I said that these two lines have to intersect while these bits are still in some distance one from the other, it's easy to understand it when we will do another iteration and we will see what's going on. So let me do the same example but one iteration more. As you can see here, when we have only one positive bit and one negative bit, in next iteration this negative bit is omitted and only this one bit is transferred via rule number 2 to the next row. So we can say that these two bits are touching to each other. As we can see, it is very important for this process how all these negative bits are distributed. So let's have a closer look at their behavior. Definitely one thing we can say is that how these bits are distributed depends on our initial number that we are starting from. For example, if I start from a number which is constructed as alternating zeros and ones in its binary notation, like presented, this algorithm will immediately stop. Due to the special distribution of these bits, this algorithm will always immediately stop. So in case I will have alternating zeros and ones in our initial number, just after one iteration this algorithm will stop. Here we can see that this increase factor for positive bits is 3 as always, but the increase factor for this negative bits from our result is extremely high. We can see it by comparing the slopes of these two lines. So as you can see, this slope is greater than the slope of this line. Of the result, this algorithm will stop just after one iteration. Let's quickly do another example for even longer number in this form. I will extend the length of this number a little bit, adding additional zeros and ones at the end, and I will start the macro. As you can see in this example, again, we've got almost the same situation, but this line, which represents the increase factor of negative bits, has even smaller slope in this case, which means that the increase factor of negative bits is much higher, regardless how we extend this number, as long as it keeps its form and it contains only alternating zeros and ones. This process will immediately stop after just one iteration. Now I will show an example how we can get this increase factor for negative bits extremely low. To have this increase factor for negative bits as small as possible, we have to start from the number which in binary notation contains only ones, like here. Let's start our macro. Of course, all these positive bits are aligned, reflecting an increase factor of 3 for all these positive bits. On the other hand, what we can see here for these negative bits that contribute to our result, we can see an increase factor of 2, but only for some initial number of bits. The increase factor of 2 is the smallest increase factor that we can achieve. We have at least shift by one column from iteration to iteration. So if we have shift by one column from iteration to iteration, then we have an increase by a factor of 2, like in this case. Please notice that we can influence only some number of initial bits. The longer we make this initial number, created only from ones, the bigger number of initial iterations will fit into this increase factor of 2. However, when we will continue our iterations, we are unable to keep this increase factor by 2 longer, and in the following iterations we will always have random changes like visible here in this area. Please notice that by starting from a specially prepared initial number, we were able only to influence our result to this level. And the number of these initial small steps is the same as the number of bits in our initial number. So the conclusion is that we are only able to influence a certain number of initial iterations, the limited number of bits at the beginning, but later chaotic changes are taking control over this process. When we will take into consideration all these elementary increase factors, we can see that at the end, this average increase factor through all these negative bits is again greater than 3. Let me present another similar example starting from the number which in binary notation will contain only ones, like here. But to process this number properly, I have to zoom out a little bit. And now we can start. To save time in all following examples, I will immediately jump to the result, skipping this whole procedure when the result is generated. So what do we have here? Of course, we've got this straight line going through all these positive bits, which represents a horizontal increase factor of 3. For a certain number of initial iterations, we can observe a horizontal increase factor of 2, represented by this line going through these negative bits from the result. As you can see, the slope of this black line is steeper than the slope of this red line, which means that this black line has a smaller horizontal increase factor than this red line. In this case, we've got here a horizontal increase factor by 2, and here for this red line, as usual, a horizontal increase factor by 3. And here again, we were only able to influence this process through a certain limited number of initial iterations, more or less to this level. As you can see, after this initial number of iterations, this process becomes chaotic, and as I will show in a moment, is governed only by the probability rules. Because of the chaotic distribution, we can see sequences of increases by a factor of 2, like for example in this area, and the same here. But we can also see very high increase factors, for example here. I will zoom in a little bit to show some important features of this process. We see small sequences with an increase factor of 2, for example here or here, but also some pretty high increase factors, like for example here, where we can see a shift by a bigger number of columns per one iteration. As we can see here, even though we are able to influence a certain number of initial iterations, to have at the beginning increase factor of 2, like in this area, after a while the behavior of these bits is governed by chaos, and we see random elementary increase factors. Sometimes we see increase factors of 2, sometimes much bigger. But the average increase factor of these negative bits in this area, in this chaotic area, is greater than 3. We can see it by comparing slopes between this black line and this red line. As we can see, the average increase factor in this area is greater than 3. Looking at this whole process from beginning till the end, represented by this green line, we can say that the average increase factor of all these negative bits from our result is still greater than 3 by comparing slopes of this green line and this red line. Now I will quickly explain how we can check or calculate this average increase factor. Let's say we want to find this average increase factor, and we have delta R, which means total number of rows, and each row is one iteration. So the total number of rows means how many iterations we've got in the whole process. At the same time, we've got delta C, which represents total number of columns, how many columns we went through in the whole process, or what is the difference between the last column and the first column. So let's say that we have P, which is delta C over delta R. In this case, our average increase factor will be 2 to the power P. So we are just checking what is the ratio between the total number of columns and the total number of rows. And the average increase factor is 2 to P. Just for example, if the number of columns is the same as the number of rows, which is the same as the total number of all iterations, if these two are equal, then P is 1, and we've got the the average increase factor equal 2. When the number of columns is twice as big as number of rows, we've got P equal 2 and the average increase factor is 4. If the number of columns is 3 times the number of rows, then P is equal 3 and our average increase factor is 8. What will be the situation if the average increase factor is 3? Like here. If we've got the average increase factor equal 3, it means that P should be 1.585 and then the number of columns should be 1.585 times number of rows. We can check if this is correct based on our last example. We will check the increase factor for these positive bits. Now I will check how many columns and how many rows we've got in this process. Starting from this point, I'm checking the number of columns and the number of rows. As you can see, we've got 336 columns and 212 rows, which represents the full process how all these positive bits are growing. When we divide 336 by 212, we've got 1.585 and 2 to the power 1.585 is exactly 3. That's the reason why I can say that this increase factor for all these positive bits is equal 3. Now I will check the average increase factor for all these negative bits from the beginning till the end. So I'm starting from the beginning and I'm checking the total number of columns and the total number of rows in this process. As we can see, this time we've got 382 columns and 212 rows. As we can see, the ratio between the number of columns and the number of rows in this case is 1.8, which means that the average increase factor for these negative bits in this case is 3.48 and it is greater than 3. And that's the reason why these two lines must definitely intersect, as we can see here. Please notice that the total number of columns in our calculation is equal to the total sum of all these particular small shifts from iteration to iteration. In some cases, it is just a shift by 1. In some other cases, this shift is much bigger. Before we will talk about this chaotic behavior here, let's check if our calculation here was correct. Now I will zoom to see this result and I will use full precision calculator to check if this result is correct. First of all, I will convert this very long binary number into normal decimal number. That's our result. This is the number that we started from in decimal notation. Now I will replace this number in binary notation here and I will calculate the value of this whole number. Here we've got our result and this result should be equal to the value of our special representation generated by this macro. We can compare both. As we can see here, result is exactly the same. Now I will explain what's going on in this area where chaos governs the distribution of these negative bits at the end. We know that as we are progressing with our iterations line by line, the location of this lowest bit in next iteration depends on the location of this second lowest bit in the previous iteration, like presented now. Always, this lowest bit in the next iteration is exactly in the place above this second lowest bit in the previous iteration. We can check it here on a fragment of our previous result. As you can see, it is always the case that this last bit in next iteration is exactly above the second lowest bit in the previous iteration. In every single case, the situation is exactly as I described. Even here, the second bit is far away from the last bit, but even so, here again, this next lowest bit in the next iteration is exactly above this bit. You can check it that it is always the case. It means that this elementary increase factor for this iteration depends on the placement of the second lowest bit in this iteration. So for example, if the second lowest bit will be just next to the last bit, we've got an increase factor of 2. But if this second lowest bit will be on a second position from this lowest bit, we've got an increase factor of 4. If it will be on a third position, we've got an increase factor of 8, and so on and so on. Now we will check what probability rules can tell us about this average increase factor. Let's say we have this single bit at the end of our row. If the situation is governed by probability rules and the laws of chaos, we can expect that on the next position we will have either another negative bit or a blank. It means that probability that we will have an increase factor of 2 and the shift from iteration to iteration just by one column is 50%. To understand this better, we will do a practical example. Let's assume that in total our whole process has 1000 iterations. So based on this first probability rule, we can say that 50% of all iterations will represent an increase factor of 2 and a shift by one column from iteration to iteration. In our case, in 500 iterations, we will have just one column per one row, one column per one iteration, which means that in all these iterations here, we will make a shift by 500 columns. This is clear, but on this side, talking about this probability, we can split it 50-50 to say that again in 25% of all cases we can expect an increase factor of 4 and a shift by 2 columns, and the remaining part is still unsure. So reflecting this in our table, in our example, we should expect 250 cases, 250 iterations with a shift 2 columns per one row. This line will cover 500 columns. So this is again clear, but here we still don't know what will be next. But we can again expect that it will be split half and half. On the next position we can find either a negative bit or a gap with a probability which is the same. So if this will be the case, we've got an increase factor of 8 and shift by 3 columns per one iteration. We will reflect this situation in our table. So keeping in mind that we are talking about 1000 iterations in total, in this case we should expect 125 cases or iterations with a shift 3 columns per one row. In total, this will cause a shift by 375 columns. And again, here we have a situation that this side is unclear. We don't know what is on next positions. We should split it in two halves in case this happens. We have a shift by a factor of 16, which means shift from iteration to iteration by 4 columns. Again, we will reflect this situation in our table in our 1000 iterations. This will happen in 63 cases, and in these 63 cases we should expect a shift by 4 columns per one iteration, and this in total will give us a shift by 252 columns. And again, because here the situation is unclear, we should expect again that this will be 50-50, so we can expect that this will happen in the half of these cases, and if this happens we will have an increase by a factor of 32 and a shift by 5 columns per one iteration. So we will reflect this situation in our table. Again, we should expect 32 such cases per 1000, and in all these cases the shift will be 5 columns per one iteration, which will give us in total a shift by 160 columns. Please notice that here number of iterations is split by half from row to row, and number of columns per one iteration is growing one by one. Because here situation is still unclear, we can expect that this process will continue, and we will reflect this situation in our table. So on the next position we can expect 16 cases with a shift by 6 columns per one row, in total 96 columns. In next 8 cases with a shift by 7 columns, which gives us 56 columns in total. In next line we should expect 4 cases with a pretty big shift by 8 columns, which will give us in total 32 columns. Again, 2 iterations with a shift of 9 columns, which in total will bring an additional 18 columns, and 1 iteration with shift by 10 columns, so in total is additional 10 columns. So when we will sum up all these columns that we achieve going through all our 1000 iterations, we can see that total number is 1999. It's great total of our process. So during this process we pass through 1000 iterations with this distribution of cases based on the random probability, which is just chaotic, not governed by any additional rules. And I will show in a moment that that's exactly the case. Through all these iterations, we will move through 1999 columns from beginning till the end, which brings us to the conclusion that total ratio between the number of columns and the number of rows for all these negative bits at the end is equal to. Because of this, we can say that the average increase factor in this process is equal 4. So as you can see here, it means that if this process is chaotic, we should expect this distribution of cases of different elementary increase factors to occur, and for the final average increase factor to be close to 4 or tends to be 4. Now I will present a few practical examples where you will be able to see how this average increase factor for all these negative bits tends to be 4. Here you've got an example for this number, and as you can see, this example is generated in mode 4, which means that on the positive side we always have a substitution 3 is equal 4 minus 1, which produces this line which represents an increase factor by 4. We can also see, as usual, this red line which represents an increase factor by 3. And it was explained previously that when we've got one positive bit at the end and a sequence of consecutive negative bits, we can substitute it with one positive bit at the end. So we know that this line represents an increase by a factor of 4. And this line represents an increase by a factor of 3. Now I will shift this line to see what's going on at the end of each row through all these negative bits that constitute our result. I will take this line and shift it at the end. These negative bits are not fully aligned with this line. They are sometimes going a little bit up, sometimes a little bit down. This distribution is chaotic, but looking at the average increase factor, we can clearly see that it is here like 4, that the average increase factor of all these negative bits is 4. Let me present this second worksheet here, where certain statistical information from this process is collected. I will briefly explain what we see here. In this column we have different elementary increase factors. The shift in columns per one iteration. So for example, if we have one column per one iteration, it means that we have an increase factor of 2. If we have 2 columns per one iteration, it means that we have an increase factor of 4, and so on and so on. So in this column we have how many iterations were counted with a specific increase factors. Looking at this first row, we have 52 cases with a shift by one column per one iteration, which means an increase factor of 2, and it happened 52 times in this example. Here in the next line we have 25 iterations where the increase factor was 4, which means that there was a shift by 2 columns per one iteration. And still we've got 10 cases where there was a shift by 3 columns per one iteration, which means an increase factor by 2 to the power 3, which is 8, and so on and so on. Here at the end we have one case where the shift was 7 columns per one iteration, and we can search for this particular case in our example just to show you what we are doing here. I believe that this case is here. We can count that here in this iteration we have a shift by 7 columns in one iteration. 1, 2, 3, 4, 5, 6, 7. So as you can see here, we've got in one iteration a shift by 7 columns at once. Okay, we can go back. Here in this column we have a predicted number of cases. Based on previously presented statistical distribution of cases, we should expect that an increase factor by 2, which is a shift by 1 column per one iteration, should represent a half of the cases. This should be 1/4, 1/8, and so on and so on. So it should be halved from one line to another. This should be the case, but because it is chaotic, we should not expect that this situation will really appear in reality, but there can be small deviations from these numbers. This is predicted number of iterations for each elementary increase factor as we have them here. In the last column, we have total number of columns the last bit was shifted by in all cases with a particular increase factor. Because in the first row we have 1 column per one iteration, it means that during our 52 cases we observe a total shift of 52 columns. In the second row, there is a shift of 2 columns per iteration, which means that across our total of 25 cases, we have a total shift of 50 columns, and so on and so on. Here in the third row, we have a shift by 3 columns per one iteration, and we have 10 such cases, 10 iterations with this increase factor. So it means that in total, we shifted this last bit by 30 columns. Here in this table, we have the total number of all iterations, which is the sum of every element in this column. So it's 102 iterations in this example. Here we have the total shift in the whole process. For all negative bits, it is the sum of all numbers in this column. And based on these two numbers, we can calculate the average number of columns per one iteration. The average shift of this last bit in columns per iteration. And based on this shift, we can find the average increase factor, which is 2 to the power a. And this number is expected to be, first of all, definitely greater than 3 and tends to 4. But because our process can stop earlier, it can be less than 4 in many cases. Yeah? But in this case, it's actually 4. And in this graph, we see for each elementary increase factor, we have a number of cases in comparison to predicted values. So this gray line represents predicted values, and the red points and the red line represent real values from this case. As we can see, distribution of numbers of different increase factors is pretty close to predicted values. The more iterations we will have, the longer the process will be, this will be closer to predicted values because statistical distribution will be closer to values that we predicted. Let's check another example. Here we have our initial number in binary notation. It's pretty long number. And as you can see, the result of this process with a line that represents an increase factor by 4. We can easily see that in this case, this average increase factor is much bigger than 4. That's the reason why for such a big number, this process ends so quickly, because the average increase factor for negative bits is much bigger than 4. Let's check the statistics for this process. As you can see, in this case, the average increase factor is greater than 5. And we can see here that for different elementary increase factors, our real results are bigger than the predicted values. That's the reason why this average increase factor is greater than 4. Obviously, it can be much greater than 4, which is absolutely fine, but definitely it is always greater than 3. Here we have another example for this initial number in binary form. And we've got our line which represents an increase factor by 4. In this example, we can observe how these negative bits fluctuate around this line. Sometimes they are going a little bit higher, sometimes a little bit below. And here again, in this case, the average increase factor of all of these negative bits from our result is greater than 4. We see it clearly because this line should start from this point. Let's check the statistics for this case. Here we see that in this case the average increase factor is greater than 4. And we see that for particular elementary increase factors, sometimes our real results are below the predicted values, sometimes above. But on average they are very close to our predictions. Let's consider another example. In this example, we started from the number which in binary notation contains only ones. And as you know from previously presented examples, in such a case, at the beginning of the process, we should expect a long sequence where each elementary increase factor is precisely 2, which we clearly see here. But starting from this point, from this iteration, we see during the following iterations that the average increase factor is like 4. Here we've got this red line which represents the average increase factor by 4. And I will now shift this line here to see how these negative bits will fit into this line. And we can clearly see that starting from this point till the end of the process, we see an average increase factor which is greater than 4. But for the whole process, starting from the beginning till the end, an average increase factor is definitely less than 4. But we can also be sure that it is greater than 3. So we can check the statistics for this result on another worksheet. In this case, we have an average increase factor 3.5, which is greater than 3 as expected, but it is less than 4. Because of much bigger number of cases, that represents an increase factor by 2, which was specially produced by carefully selecting our initial number. In this example, we see that the number of iterations with the increase factor by 2 is 2/3 of all cases. Usually we should expect that it is around half of the cases, but here it is 2/3. And that's the reason why these results are below our prediction. But even though we specially created a kind of worst case scenario, the average increase factor in this case is 3.5, which is enough for this process to stop. Now, let me show you our last example, which is a little bit extreme one. So I started from the number which in binary notation is extremely long. As you can see here, this number is like very, very long. And I already generated this example. But before I will show you the result, I want to check using full precision calculator from the internet if this result is correct and how extreme this result can be. So here I have these calculators from the internet. So I will start from the conversion of this number to decimal form. So I will copy this whole number here. This is our initial number in decimal form. And now I will check the result. So on the left side of the equation, we've got this number multiplied by 3 to the power 1168. So I will do the same in the full precision calculator. I need to extend decimal precision. Okay, so I see this is the result on the left side of the equation. And then on the right side, I've got this number generated here by the application. So let me copy this whole result to another instance of this calculator. So this is the result. So we can compare both. We can easily see that this number is exactly the same. So it means that the result was produced properly. Now I will show you a graphical representation of this result. I need to zoom out to the maximum. As you can see, I am not able to show you this result fully because it's too big in this Excel and I am not able to zoom out more. But again, this red line is representing an increase factor by 3. And on the negative side, at the end for all these negative bits, we have here this black line which represents an increase factor by 4. It is not absolutely aligned with the result that we've got, but it is very close. It is a very long process, so we can shift these two lines to check how this process ends. On negative side, we've got increase factor which is not exactly like 4. But it is definitely higher than 3. So let's check the statistics. As we can see, the total number of iterations in this example is 1168 and the average horizontal increase factor is 3.88. This result is pretty close to our predicted values. As you can see here, the differences between our predictions and achieved values are really very small. So it looks like that our predictions are really very accurate in this case. Let's talk for a moment about this whole process. Let's assume we've got a number in extended binary notation in our two-dimensional representation of numbers. At the top, we've got powers of 2, which are represented as columns and the letter C. So these are our powers of 2. On the left side, we've got iterations, which are represented as rows. So every row is another iteration going in this direction. We learned from a few of our past examples that this positive bit at the top of our binary representation of our extended binary number is growing with an increase factor of 3, which means that we've got an increase of 1.585 columns per every iteration. It was already presented a few times, so you should exactly know what does it mean. So when we progress with our iterations, this positive bit will follow through this line, and this line represents exactly an increase by 1.585 columns per iteration. So this should be clear. On the negative side, as it was also presented, we've got an increase by a factor of 4 on average. So it means that we should observe on average an increase by 2 columns per one iteration, per one row. So comparing these two lines, we can say that subtracting these two numbers, we've got 0.415, which means that when we are progressing with our iterations, on average, the length of this number in extended binary notation should shorten with this decreased speed, should be shortened by 0.415 column per one iteration. So this should be the decrease speed of the length of our number in extended binary notation as we are progressing with our iterations. But we should not forget that we are talking about a process which is also described by this formula 3n plus 1. And what does it mean? How can we see this formula here? So from this formula, when we are talking about a number in binary notation, we can say that first of all bits are multiplied by 3 by this. So 3n means that all our bits should be multiplied by 3, but the lowest bit is multiplied always by 4 in standard Collatz process, because if we will multiply an odd number by 3 plus 1, it means that the lowest bit in this number is actually multiplied by 4. And we can see exactly this formula, how this is applied here. So we've got this all bits multiplied by 3 here, which is the increase factor that is applied to entire number. But the lowest bit is multiplied by 4, and that's the reason why in our case also this lowest bit increases on average with a factor of 4. Of course, this process is a little bit chaotic, and we should not expect an exact alignment of these negative bits at the end with this red line. But on average, this process is pretty accurate. And to check this, I did a very extreme example. So I started from a randomly generated binary number, which was 20,000 bits long. It means that this number was of order of magnitude, like 2 to the power 20,000, an extremely big number. Based on our previous result, we should expect when iterating this number, we should see decrease of the length of this number by 0.415 column or bit per iteration or row when iterating this number. So based on this rule, we can easily predict when this number should decrease to 1 or should reach 1. We can calculate that this number should reach 1 after 48,192 iterations. In reality, when I checked this number, it was 48,044 iterations. And this result is pretty accurate. So the difference between my prediction and reality was around 0.3%. It means that this rule about how fast a number should decrease in length is really correct. We can visualize this process, and we see that starting from a number which contained at the beginning 20,000 of bits, we decrease this number going through 48,044 iterations till 1. And this line represents the length of this number at each iteration. And as we can see here, it's straight. It looks like it is a straight line. But when we will have a deeper look or zoom out, let's say this initial part, which is just the initial 4,000 of iterations, we can see that it is not so straight. There are some disturbances on this line visible. So now we see only the initial 4,000 iterations. But if we will zoom even more to the initial 400 iterations, we see that it is not a straight line, but rather we can see a chaotic behavior in this line. When we will zoom even more, let's say to 100 iterations, we see that the length of this number changes in a very disturbed way. But looking at the overall picture of the whole process, this line appears to be straight. But in actuality, it is disturbed, and we can only see it when we zoom in. Then all these small deviations are visible. When we see this whole process, we see that it is governed by very strict rules. So on average, the length of a binary number is shortened by 0.415 bit per iteration. And it is really very nicely visible when we will start from a big number, that it is going smoothly down. Here we can see the statistics for this example. As we can see, the total number of iterations was 48,044. And here we've got the distribution of different elementary increase factors. And in the next column, a number of cases in which that particular increase factor appears. As you can see, in one case, there was an increase factor 2 to the power 17 and a shift by 17 columns from iteration to iteration, which is quite a lot. As you can see, the distribution of elementary increase factors is almost exactly as predicted. And also, the total average horizontal increase factor is 4.00, as you can see here. I think we are ready to answer our last question. Can we construct this representation for any number? As it was presented, when we start this process for any initial number, we can only influence a limited number of initial iterations. And we can have this influence in two different ways. Either to shorten this number immediately to 1 and stop the process, or extend the length of our initial number a bit. But after this initial number of iterations, this process follows very strict probability rules. And because of this, following these rules, the length of a binary number is shortened on average by 0.415 bit per iteration. Therefore, after a series of iterations, an expected representation of the initial number is always created, and this process will always stop. So the answer to this question is yes, we can construct this representation for any number. We started this presentation from this special formula which presents required representation of the number, and we learn how to construct this representation for a number. We learn also why this formula is important for Collatz conjecture, and finally we show that we can construct this representation for any number. Summarizing all these 3 points, we can conclude that the Collatz conjecture is true. Moreover, we can also predict how fast a number can reach 1, how many iterations we need for a number to reach 1. Thank you very much for watching. I believe that now you understand why the famous Collatz conjecture is true. If you enjoyed this presentation, you can buy me a coffee at this link. Also, you can download the Excel macro presented in this video from this link. Here is the link to the paper which contains the very strict mathematical proof based on ideas presented in this video. I also recorded another video, the Proof of Collatz Conjecture Explained, which you can find at this link, where this strict mathematical proof is explained in detail. If you are interested in some of my other papers, you can find them under these links.